Now. Okay, then welcome everyone. So this is the DutchCATS seminar, the Dutch Categories and Types seminar, where we try to get people, well, mainly the Netherlands, but now maybe also in Belgium, who are interested in type theory and category theory together and get to know each other a bit better and their work. So as Benedict also said, I mean, the previous time we tried this, we had this on location, which was, I think, a very nice event. Now, unfortunately, because of all the pandemic situation, I think we are back to doing this online. Yeah, I still hope we can keep this DutchCATS alive, and I'm very happy to have Julia as a first speaker of the new year, so to speak. Yeah, she's going to talk about some work in category theory, about exponentiable Grothendieck abelian categories in algebraic geometry, and I'm very curious what she has to say, so please go ahead.
Okay, thank you very much. So first of all, I would like to thank Benno and Benedict for the invitation to talk. And so what I'm going to talk about is indeed exponentiable Grothendieck abelian categories, and in particular, how we see this in algebraic geometry. And this is joint work with Ivan Diliberti, who is also among the audience. So he can maybe assist me with some questions if necessary at the end. Okay, so let's get started. So first, let me recall a little bit what Grothendieck categories are and the way we're going to look at them along the talk. So a Grothendieck category is just an abelian category, which is co-complete, meaning it has all small co-limits, and it has a generator and exact filtered co-limits. So filtered co-limits commute with finite limits. And the main example of Grothendieck categories are precisely module categories. So if we have a ring R, the category of right R modules or left R modules, well, we will choose right along the whole talk. It's a Grothendieck category. Why do I call this the one object case? Well, we can always see a ring as a category with one object, and the endomorphisms of that object be given by R. So that would be a category enriched over abelian groups with one single object. And then we can actually do this story for the several object case, which instead of being one object up enriched category, we take a small up enriched category, and we take the up enriched pre-sheaves. So mainly functors, linear functors from A up to abelian groups. And this is precisely the analog of the one object case. So this is also a Grothendieck category, and we will call it the category of right A modules and denoted by mod A. So this is our main example. And there are two perspectives that we will take to look into Grothendieck categories today. The first one is that Grothendieck categories are actually the up enriched topoi. And let me go a little bit in more detail. We have that Bourseau and Quinteiro developed a theory of enriched sheaves in certain for enrichments in certain categories, for which in this story we just have to know that abelian groups satisfies their conditions. So we can apply their theory to abelian groups, so abelian enriched, categories enriched over abelian groups. And the theorem in that particular setup would say the following: there is a one-to-one correspondence between left exact reflections of these enriched pre-sheaves and up enriched Grothendieck topologies, which is a linearized version of what the classical Grothendieck topology is. And the bijection comes, if you take a Grothendieck topology, you take its category of sheaves, and this gives you a left exact reflection of the pre-sheaves. And then if you have a left exact reflection of the pre-sheaves, there's a way to cook up actually a Grothendieck topology such that your initial category was sheaves over it. So we do have a good theory of up enriched sheaves or up-enriched topoi. And those are indeed, we have, because of this bijection, you have categories of sheaves on a Grothendieck abelian site or left exact reflections of categories of modules. And there is a theorem, a very important and classical theorem in abelian categories, which is Gabriel-Popescu result, that says that Grothendieck categories are precisely the left exact reflections of the categories of modules. So what we conclude out of these two things is that actually up-enriched topoi are precisely the Grothendieck categories. And this perspective, combining the sheaf interpretation of Gabriel-Popescu theorem, was first done by Wendy Lowen in her generalization of the Gabriel-Popescu theorem. So we have this perspective of Grothendieck categories. We can see them as the up-enriched topoi, but we will also use another geometrical perspective on them. So for this, let me recall a little bit the main idea that we will be using, from classical algebraic geometry. So we have an interplay between algebra, geometry, and also category theory in classical algebraic geometry. In here, if you start from a ring, of course, you can take it a spectrum and actually the associated affine scheme, and we can do geometry there. And also we can associate the category of quasi-coherent sheaves, which in the affine case actually is just taking the modules over the initial ring. And we know any scheme is just a gluing of affine schemes. So of spaces which are spectra of rings, of commutative rings. But one may wonder, okay, do we have such a nice interplay when our algebra is non-commutative? Can we still use geometrical methods to study non-commutative algebra and so on? Well, one approach to see this, we don't have a spectrum available anymore, but we still have category theory information. So this is the approach we will take today also in order to look to non-commutative algebraic geometry. The main idea is that all you need is to have sheaves. And this is kind of the philosophy that Grothendieck actually had and mentioned several times in his works is, okay, in order to do geometry, you don't need the space itself. You just need the category of sheaves on the space to be. And this philosophy will fit very well into this story today. We have first this theorem of Gaber that says if you have a classical scheme, the category of quasi-coherent sheaves is the Grothendieck abelian category. So Grothendieck abelian categories will be what we expect to represent our schemes. And this is indeed in that framework of Grothendieck's philosophy, because we have the reconstruction theorem by Gabriel and Rosenberg, which says that we can fully recover the geometry of a quasi-separated scheme from its category of quasi-coherent sheaves. So we can do geometry using the sheaves, and we can always recover, if we were working with a scheme, the scheme out of it. So the philosophy we will be working with today is that Grothendieck categories are actually categorical models for non-commutative schemes. If you know it came from a commutative, so a classical scheme, you can recover it, but you may have more that will be representing non-commutative spaces. And for example, the non-commutative affine schemes are precisely the categories of modules. Very well. So we have these two perspectives between in order to see and to interpret Grothendieck categories. But what about the morphisms between them? Well, we can define a category, a two category of Grothendieck categories, GRT, which will be, okay, the objects will be Grothendieck categories. The one cells will be the up-enriched left adjoints, and the two cells just the natural transformations between them. What is the geometrical interpretation of these two categories? Well, we have precisely that if you have two schemes, a morphism between schemes provides an adjunction between the categories of quasi-coherent sheaves. And this is the direct inverse and the direct image and the inverse image adjunction. But as you see in here, if you want to have also the perspective from up-enriched topos theory, in there, geometric morphisms are not just left adjoints, they are left exact left adjoints. So in that setup, we introduce another two category, GRT flat, Grothendieck flat. The objects are still Grothendieck categories. The one cells are now left exact left adjoints. If you want, well, normally the direction is given by the right adjoint, like in the classical case of geometric morphisms. So these are adjoint pairs where the left adjoint is left exact. And then the natural transformations are between the left adjoints. And now these two categories does actually fit into both perspectives that we have when we're looking at Grothendieck categories. On one sense, they do still have a geometrical meaning. They mimic the behavior of this direct inverse image adjunction that we had, but when the morphism of schemes is flat. So flat morphism of schemes do give rise to this type of adjunctions where the left adjoint is left exact. And on the other hand, this is just precisely the up-enriched geometric morphisms. So somehow this is the framework in which up-enriched topoi at the same time can be seen as non-commutative spaces and flat morphisms between them. And this is why we called these adjunctions with left exact adjoint flat morphism. And this will be our two category of study in this talk, which is, as I say, can be seen as non-commutative schemes with flat morphisms or up topoi with up-enriched geometric morphisms. Well, these two categories happens to have a monoidal structure, which actually has a geometrical interpretation. So let me go through that. And this is the first result of the talk. And for that, let me revise first the tensor product of locally presentable categories. So Bert and Kelly introduced, well, Bert in his thesis using Kelly's previous results, introduced a tensor product of locally presentable categories, where he takes the two categories with locally presentable categories as objects and one cells given by the left adjoints, and then natural transformation between those. He shows this is a monoidal closed to category with the structure, monoidal structure given as follows. If you have C and D, two locally presentable categories, their tensor product is given by the right adjoint functors from C up to D. This monoidal structure has as unit the category set of sets. The internal home is given by the left adjoint functors, so it's actually coinciding with the external home, the internal home. And the monoidal structure is actually symmetric. So if you have a right adjoint between C up and D, you just can take its corresponding left adjoint and the op of it, and this will be also a right adjoint from the op on C. So this is actually an isomorphism. Well, this is all in classical category theory, not enriched, but it translates immediately to the enriched setup. So in here, I just change everything by its up-enriched setup, and it works the same. We have the tensor product given by the right adjoint up-enriched functors between C up and D. The change in the unit now instead of set is up, and all the rest works the same and carries through the same way. So we have this tensor product, this monoidal two structure. And in the classical setup, we know that Grothendieck topoi are in particular locally presentable categories. While in the up-enriched setup, we have that Grothendieck categories are in particular locally presentable up-enriched categories. And then let's go back to the classical setup. We have a theorem by Pitts that says that this tensor product of locally presentable categories actually restricts to a monoidal symmetric structure in topoi. And this monoidal structure is precisely the Cartesian monoidal structure in topoi. So it's Cartesian product. So the tensor product as locally presentable categories of two Grothendieck topoi is again a Grothendieck topoi, and it induces a monoidal structure in topoi. We have, and we proved this a while ago, a similar result for the up-enriched case together with Wendy Lowen and Boris Shoykets. And it's precisely that the tensor product of locally presentable up-enriched categories restricts to a monoidal symmetry structure, but not in topoi, in GRT. So with the left adjoints without requiring left exactness. And this monoidal structure is actually not the Cartesian monoidal structure. It is really a honest monoidal structure, it's not the product. But of course, we are interested in the flat case, what happens. And before I go there, let me first introduce indeed that, show that this tensor product actually has a geometric interpretation. And this is given by this theorem of Brandenburg that says if you have two quasi-compact, quasi-separated schemes, then the quasi-coherent shifts of the product of X and Y is equivalent to the quasi-coherent shift of X tensored with the quasi-coherent shift of Y. So we can actually see this tensor product as the product of non-commutative schemes. Somehow we had the product in the commutative classical setup, and this is precisely given by the tensor product in the categorical perspective, in the categorical models of these schemes. So we can interpret this tensor product as the product of non-commutative schemes. But what happens if we have flat morphisms? So if we are in our two category of Grothendieck flat, well, we do prove that this tensor product also endows these two categories with a monoidal, symmetric monoidal structure. And how do we prove this? We of course know already that the tensor restricts to Grothendieck categories because of this previous theorem. So you only have to check the factoriality of the tensor product, namely that this assignation amounts to a factor from Grothendieck flat times Grothendieck flat to itself. I have put here cont instead of right adjoint, because from now on we will always be working with Grothendieck categories, and then the adjoint factor theorem tells you precisely that limit preserving factors are the right adjoints and co-limit preserving factors are precisely the left adjoints. So here is just limit preserving factors or equivalently right adjoints. So that's why I changed here the terminology, but it's the same. So we have to prove the factoriality, which from the geometrical perspective is really proving that the product of flat morphisms is flat. This is true in the classical setup, and now we are proving it in this categorical non-commutative framework, so to say. And how do we do this? Well, we have an implicit description of this adjunction, and it's given as follows. If you have, I will give it for just tensoring on one variable, then you can extend it to the two variables just by composing. So it's not a problem. Let A be a Grothendieck category, and then take this a flat morphism, where the direction is the one of the right adjoint. We define the right adjoint identity of A times F as follows. It has to go from the product of A times B to the products of A times C. Here I already wrote the formula. And how do we define it? To every S limit preserving factor, we compose with the image F lower star, which is the right adjoint and also limit preserving. So this is well defined. It lies in the limit preserving factors. On the other hand, you would be tempted to define the left adjoint in the same way, taking S in the continuous factors from A up to C and composing it with a left adjoint. But the problem here is the left adjoint is a priori and in principle not preserving all limits only finite ones. So this does not lie in limit preserving functors anymore. But let me call it one intersection F upper star, because it will help us to build the left adjoint, which is actually given as follows. We take this functor here. We put here an underline. It's actually a size issue. I won't get into this, but we don't take just in all functors from A up to B. We take the small functors, and this lies in a small functors. And then limit preserving ones are the embedding here has an adjoint, and this is the one we take here. So this composition actually gives you the left adjoint, and this is the explicit description of this adjunction. But the problem is, from this description, it is very hard to see whether this is actually left adjoint. Sorry, left exact. That's what we want. We have an adjunction, but we want that the left adjoint is left exact in order for it to be a flat morphism. So a priori it's hard to say. So we need a nicer description of this guy in order to see that this is really left adjoint, which is left exact. And how do we do it? Okay, we have the same data as before. A, Grothendieck category, F, a flat morphism. We know that A is a Grothendieck category, so in particular, it is locally presentable. So there exists some regular cardinal such that A is the int alpha completion of its alpha presentable objects. So we have this expression of A. And the int alpha completion is reflected in pre-sheaves. So we have a reflection here. So in particular, it's a flat morphism, but with the direct image being fully faithful. This is fully faithful. It's an embedding. Then we prove that this left adjoint is actually up to ISO, given by the following. So we have, this is the map. What we do is first we fix C, and we just use the reflection we have here. So we do G times identity, right adjoint. Then we do the left adjoint, but when our first category is no longer a random A, is a module category, and then we go back using the left adjoint of this guy. Why is this helpful? Well, I will go, I won't go in much detail, but from here, we have this guy is a right adjoint, so it is left exact, no problem. This guy, which in the general case had this complicated, let's say, or not very explicit description, in this particular place, because we're working with modules in this argument, it has actually a very nice description that one can prove, and is that these continuous functors from mod A alpha up to C are precisely the left exact functors from A alpha up to C, because modules are just the free completion under co-limits, under small co-limits of A alpha. So using that, you have that these two categories, this one is this one, and this one is this one. And then you just send every left exact functor to the composition with F upper star. And this is left exact by definition, because F was flat, this was left exact. So this is well defined, and it's actually the left adjoint. So in the case of mod A, we have a very nice description of this. And now another thing that we managed to prove is that G, that remember was this embedding, this precise flat functor, the int completion inside mod, when tensoring, gives us again a left exact reflection. So it is in particular flat. I won't get into the details, but we can prove it. So by decomposing this guy in the three compositions, we can prove that each of the components is left exact. So our left adjoint is left exact and indeed flat as we wanted. So we do have a monoidal structure in Grothendieck flat. Very nice. So when we have a monoidal structure, one may wonder, what are the exponentiable objects? Well, one would like to have an inner home, but we don't have an inner home in this case, but we will characterize, and that's what for the remaining of the talk, the exponentiable objects in Grothendieck flat. We will follow mostly a parallel argument to the characterization of exponentiable Grothendieck topoi, which was given by Johnston and Yoya. So I won't mention it in any, but it's more or less a linear parallel of their argument. So let me go through it. First, what is an exponentiable object? Well, in the particular case of our monoidal structure is the following. A Grothendieck category is exponentiable if the functor tensoring with it admits a right adjoint. Or in other words, if for every Grothendieck category B, there is a Grothendieck category B to the E, such that we have this natural in A. So A times E to B flat morphisms are the same as flat morphisms from A to B to the E. So we can pass, if you want, the E from the first to the second argument. And so our goal is to characterize these exponentiable objects. And what is the geometrical counterpart of all this? Well, if we take the category of schemes with flat morphisms, the two categories, well, then natural transformations between those flat morphisms, then this question of characterizing the exponentiable objects is just the non-commutative parallel to the question of characterizing the schemes X, such that for any other scheme Y, there is such a Y to the X with this isomorphism. So flat morphisms from Z times X to Y is the same as flat morphisms from Z to Y to the X. And this is natural in C. So it is a non-commutative parallel to trying to find a flat inner, a flat home scheme, if you want. So let's start with a first approximation. So we prove this lemma, which says that we can, to check exponentiability, we can reduce ourselves to check it in a certain family of Grothendieck categories and not for every base. And it is the following family. A Grothendieck category is exponentiable if and only if for every small category A, the exponential mod A hat E exists, where A hat is just the free completion of A under finite limits. So you take your A, you complete it under finite limits, you take their modules, and those, if this exponential exists for all of those, then E is exponentiable. It exists for any other base that we may take. How do we prove this? Well, very roughly, the argument is the following. Given any Grothendieck category, C, you can actually write it in Grothendieck flat as a pullback of categories of this shape. And actually it can be chosen by taking A, a set of generators of C. Then you take its finite limit completion. You can find also a B and a C and such a diagram, which is a pullback. And now we have that exponentiability as a right adjoint, it commutes with pullbacks, which are finite limits. So the main idea is, by assumption, we know that mod A hat to the E exists, and the same for mod B hat and mod C hat. So we have these three exponentiable. We take its pullback, and that pullback will be precisely C to the E. It will have the universal property that we require. And that's a bit the argument behind the proof. So we have that it's enough to check it in this type of basis. So this gives us already a very big and important family of exponentiable objects, which is precisely the affine non-commutative schemes or the up-enriched presheaves, if you want. So modules over B are exponentiable for any small category B. How do we prove this? Well, because of the proposition, we know it's enough to check it for all the bases of this shape. And the claim is that this exponentiable is precisely this one, is the modules over the tensor of A times B up and completed under finite limits. This tensor is just the linear tensor product of linear categories, of up and rich categories. So it's objects are just pairs of objects, and morphisms are tensor product of morphisms. And this is a monoidal structure in up enriched small categories with inner home just the up functors. So the up enriched functors, like some sort of replacement of the Cartesian tensor, the Cartesian product of small categories. So let's prove this claim. We have flat morphisms from C times mod B to mod A hat. First of all, this tensor product, it's an easy computation to see that it's nothing but up enriched functors from B up to C. You just take the definition of this and a couple of using that modules are the co-limit completion of B and so on. It's very easy that you end up with this. Now, what are flat morphisms? They are just the adjunctions. So the with a left adjoint being left exact. So co-continuous means left adjoint and lex is left exact. So basically the flat morphisms had the direction of the right adjoint, and in here we are taking the left adjoint, so we have to reverse the order of the, but there's nothing but the definition of flat going on here. So you have from mod A hat to B up to C. Now, mod A hat, first co-continuous from mod to something is just morphisms from that A hat, sorry, to whatever we have here, because mod is just the free completion under small co-limits. So then we have just lex functors, so left exact functors from A hat to this. But A hat is the free completion under finite limits. So left exact functors from that completion to this is just functors from A to this. And then we use the tensor product to bring the B up here. So this is nothing but functors from A times B up to C. And now again, we complete under finite limits, and that's why the legs appear. And then we complete under finite co-limits, and that's why the co-continuous appears. And this is nothing but flat morphisms from C to this guy, showing what we wanted. Okay, so we have that pre-shift categories are all exponential. And we will use along the way very frequently what we call the up enriched object classifier, and I will explain in a second why. We have this proposition, the forgetful functor from flat Grothendieck up to categories, which is just we send the Grothendieck category to itself, seeing as an up enriched category. This is representable. And the object representing it is precisely the modules over the finitely presented abelian groups up. And why the terminology? Well, in classical topos theory, you have that this functor from topo up to cat is represented by the topos set O, which is the classifying topos of the geometric theory of objects. So in parallel with that setup, we denote our representing, if you want, object as up O. And this is, as the proposition says, is mod of finitely presentable abelian groups up. So in particular, what does this mean? This statement is that for every Grothendieck abelian category, we have that the flat morphisms from A to ABO is just A. And this will be very useful along the way. A second approximation, we know that to check exponentiability, it's enough to check it in mod of A hat. Well, we can reduce it further. it's enough, and that's what this lemma says, it's enough to check it in this base, only for this base of app O, so the object classifier. How do we prove this? Well, obviously, if E is exponentiable, this guy exists. We prove the reversed, the reverse direction. So if this guy exists, we want to prove that this guy exists for any category A, a small one, because then by our proposition of before, we conclude. And the claim again is, okay, this exponential is given as follows. We take this exponential that exists by assumption, and then we take a further exponential that we know by the previous proposition. We know that the pre-shifts are exponential, so we know this guy exists. So we claim that this is the exponential that we're looking for. And how do we prove it? Well, flat morphisms from C to this guy using the exponentiation. First, mod A comes back, then E comes back. Then we have flat morphisms from this tensor to ABO. But morphisms to ABO is just the first, this is a representable object. So this is just the first component here. So in here, I already use the symmetry and the associativity of this tensor product. And then again, I told you before, this computation is also easy. Tensoring mod with something gives you actually morphisms from A, functors from A to that something. That's what we use here. And now, again, we complete under finite limits, and that's why the lex appears. We complete under small co-limits, and that's why the cocont appears here. And this is nothing but the flat morphisms from C times E to mod A hat, proving that indeed the E mod A hat to the E is nothing but this. So we are done. We can check exponentiability only on this base. Then it exists for any other base. And now to get the full characterization, we need to use a machinery that, as I said before already, Yoyal and Justin developed for the characterization of exponentiable topoi. And this is quasi-injective categories and continuous categories. So let me start. What is an injective Grothendieck category? An object in Grothendieck flat, we say it's injective if given such a span where G is an embedding and a flat functor. So namely, the right adjoint is a fully faithful functor, and then you have your left exact left adjoint. So that's a flat embedding. And then F is any flat functor. So for such a span, we have that there exists a flat functor H such that the whole thing commutes. Think of it as the usual definition of injective objects. This is a mono, this is any functor, and then this is any morphism, and then you can extend it to another morphism. So now our monos, if you want, are the flat embeddings. And a first example that one can prove is of injective Grothendieck categories is the pre-shift categories again. They are injective, but when your A has finite limits, not for general A, but when the A has finite limits, then the pre-shift category is an injective Grothendieck category. In particular, actually one can prove that the injective, all injective Grothendieck categories are precisely the retracts of the categories of dot shape, of categories of modules over small categories with finite limits. The proof, one direction is, imagine that you are a retract of such a category where A has finite objects. Well, we already know this is injective. And a retract of an injective is really easy to see. It is also injective. So this direction doesn't generate any problem. The other is also quite easy, but it requires to use Gabriel-Popescu theorem. So imagine you have an injective category. You take a set of generators and you close it under finite limits. You can always consider a set of generators which has all finite limits. And then you use the Gabriel-Popescu to create an embedding from A into mod of that set of generators. So you have a flat embedding here. And then you just consider the following span. You take A and its flat embedding in mod A, and you take the identity here. Then because A is injective, we have that there exists a flat H, which provides an splitting of I. So indeed, A is a retract of this guy, and we conclude. Very good, but okay, this is the result we had. Retracts of categories with finite, preshift categories of categories with finite limits. So then what this tells us is actually that the two category of injective Grothendieck categories with the flat morphisms is biequivalent to the Cauchy completion of the two category of preshift categories of module categories over small categories with finite limits and flat morphisms. This is just this, thinking the fact that if you take all splittings, then I mean, if you take the Cauchy completion of that, you're adding all the retracts, which are precisely this. Very good. But we are not quite happy with the fact that we need to take always small categories generated by finite limits. We want all preshifts. So that's why one takes this generalization, and we call a Grothendieck category quasi-injective if it is a retract of a module category with no further requirements. And this, of course, with this definition, we obtain a parallel to this. The two category of quasi-injective Grothendieck categories is precisely the Cauchy completion of the two category of preshifts, so of modules and flat morphisms. Okay, so we have quasi-injective categories as Cauchy completions of preshifts. Now let's move to continuous categories. So continuous categories started, I mean, we can trace them back to the study of exponentiable topological spaces in top. So there is this theorem by Day and Kelly that says a topological space is exponentiable if and only if its frame of open is continuous. And further, very just after that, Hyland proved this localic, if you want, version, which is that a local is exponentiable if and only if it is continuous. Then Johnston and Yoyal took this and took this definition and adapted it to categories and no longer locales. And they got the result that I already mentioned. A topos is exponentiable if and only if it is continuous. And we further have this result for infinity topoi by Anel and Leger, which is an infinite topos is exponentiable if and only if it is continuous. So we have all of this precedent work. So we will introduce continuous up-enriched categories, basically taking the enriched version of this definition by Johnston and Yoyal. And it goes as follows. An up-enriched category with filtered colimits, A, is continuous if in this diagram the left adjoint colim has a left adjoint L. So what is this diagram? A embeds into its int completion. And because A has filtered colimits, that embedding has a left adjoint, which is precisely computing the colimits, the filtered colimits. Well, we say it is this A is continuous if we have a farther left adjoint, which actually gives a very nice behavior of limits with respect to filtered colimits. So this is a continuous up-enriched category. And in particular, because this I is iota is fully faithful, also L is. That's a basic theory of adjoint triples. Very well. First example of continuous categories. Finitely accessible categories are continuous. how do you prove this? Well, a finitely accessible category is always the incompletion of its finitely presentable objects. And we can consider the natural embedding of them into A. And now, what is the left adjoint that we're looking for? Well, we have colim functor. It goes from int of A, so int of A omega, to A, which is int of A omega. And what do? Is just take the int of iota. And this gives us from int of A, so this is A, to int of A omega, which is int of A. So this gives us actually, one can check this is a left adjoint of colim, and one concludes. And this allows actually us to prove, and it's a first step to prove the following proposition, which is a characterization of continuous up-enriched categories, which says an up-enriched category is continuous if and only if it is a retract of a finitely class-accessible category with respect to functors preserving filtered colimits. Why class here? The thing is, by finitely class-accessible category, we mean just a finitely accessible category where we are allowing the finitely presentable objects to be a proper class and not necessarily a set. So that's the only difference. So we can prove, what we are proving here is that an up-enriched category is continuous if and only if it's a retract of a category of the form int of B, where B may be large. And we are not happy with it being large. And for that, to solve this, we have the following proposition. Assume A is a continuous category, and we assume there exists a small full subcategory, little a, that generates a underfiltered colimit. Then the following functor from int little a to a, which is given as follows. Just take the int of iota, goes from int little a to int big A, and then you just take the colimit functor. So this composition has a fully faithful left adjoint beta from A to int of A. So we have such an adjunction where epsilon is this functor. And this is fully faithful. And we call this a standard presentation. What we have as a first example, by the previous theorem, example, we know, actually theorem, by the previous theorem, we know locally presentable categories. They are retracts of finitely accessible categories. So in particular, they are continuous. But furthermore, they do have a standard presentation. You just have to take the A to be, if your category is locally alpha presentable, just take the full subcategory of alpha presentable objects. Those generate your category under filtered colimits. So you are fine. You can apply this proposition and you get a standard presentation. So all of this in order to get actually this proposition where we don't have that size issue of before. An up-enriched category is continuous with a standard presentation if and only if it is a retract by functors preserving filtered colimits of a finitely accessible up-enriched category, int of A, where A is small. And so if we take this as before, we can interpret it this way. The two category C and T of continuous up-enriched categories with a standard presentation, the functors being filtered colimit preserving, is just the Cauchy completion of the two category of finitely accessible categories with filtered colimit preserving functors. So we have again a characterization of continuous categories in terms of retracts, so a Cauchy completion of a certain nice category. And now we link the two. We link quasi-injectives and continuous. How? Via this theorem. There is a two equivalence of two categories between finitely accessible categories and pre-sheaf categories. And it's given as follows. S gives you to a finitely accessible category just the filtered colimit preserving functors from A to up, which is nothing than the modules from A omega up. So it is a pre-shift category. This is well defined. And PT is just taking points. That's why the notation, it maps a pre-shift category mod A to just the flat functors from AB to mod A. These are points, like in the classical setup, points are for morphisms, geometric morphisms from set to whatever we had here. This is now is from abelian groups to whatever we have here. And one can prove this way that this is an equivalence. And hence, if we take Cauchy completions, we obtain an equivalence between the Cauchy completion of this one was continuous categories with a standard presentation. The Cauchy completion of this one was quasi-injective Grothendieck categories. So that's how we obtain the relation between the two. And this will be very useful to finally prove the main theorem, which is the characterization of the exponentiable objects, parallel to the one of Johnston and Yoyal, and also the one for infinity topoi of Enel and Leger. A Grothendieck category is exponentiable if and only if it is continuous. How do we prove this? One direction is easier than the other. So let's start with the easy one. Exponentiable Grothendieck categories are continuous. Assume E is exponentiable. We are going to show that this exponential that exists because E is exponentiable is an injective Grothendieck category. To prove that, we consider an embedding, a functor here, and we want such a dashed arrow. But this, obtaining such a dashed arrow is equivalent to now using the adjunction, we have this that remains an embedding, tensoring with E remains an embedding. We have the functor corresponding to this via the adjunction. And so if we find such a dotted arrow, making this commute, then we obtain by adjunction such a dashed arrow making this commute. But observe now that the object classifier was the pre-shift category. And we have seen that pre-shift categories were injective. So this dotted arrow exists, and therefore this dashed arrow does. So this guy is also injective. Now, we have that E with the object's classifier is just the flat morphisms from E to it, to the object classifier. Now, we use that E is just E times up, and we use the exponentiability of E to pass it to the other side. So we have abelian groups, and this exponential. But this is nothing but the points of this guy. And we have proven this guy is injective. And the points of an injective, in particular, the points of a quasi-injective, but injectives are quasi-injectives, are continuous because we had this equivalence between continuous and quasi-injective via the points. So this guy is injective, applying points, you obtain a continuous guy. So E is continuous. Now let's go to the hard direction. Imagine your category is continuous and you want to show it is exponential. If E is continuous, first of all, we know it's enough to prove that this exponentiable exists. That's the first reduction we did just before introducing continuous and quasi-injective categories. First, we observe the following. Imagine this guy exists. Then it has to coincide precisely with applying S to E. E is a continuous category. We can apply this functor S. Why? Well, we have imagine it exists. Then if it exists because of the previous part of the theorem, we know it is injective. We just proved it is injective. So we can apply points to it and then back S. So, and this is because points and S were inverse to each other. This is just an equivalence. So then what are the points of this guy? Just flat morphisms from up to up O to the E. And then E passes here. So this is flat morphisms from E to up O. And because up O had that property, this is just E. So this is just S of E. So if it exists, it has to be this guy. So we just have to check that this guy fulfills the property we want. We do a small detour, and we check the case of locally finally presentable Grothendieck categories. They will be exponentiable, and then the general case. Locally finally presentable Grothendieck categories. Take a locally finally presentable Grothendieck category E. We know because of the previous step, it's enough to check that this guy satisfies the universal property. When we do check, flat morphisms from A to S of E are, S of E is just this by definition, continuous legs from this guy to A, which is just legs from this guy to A. And this taking the op out, so it will be right exact from E omega to A op, and then applying the universal property of the incompletion, you get co-continuous from the incompletion to A op, and putting the ops inside, if you want, is continuous from int op A, which is nothing but the tensor product. And now we apply the int of E omega is just E, because E is locally finally presentable. And then we apply the object classifier property. So we conclude A S of E. The S of E does satisfy the universal property that we want. Okay. So these guys are exponentiable. And now we can conclude with the general case. Let E be a continuous Grothendieck category. Then E is locally presentable because it's Grothendieck. So we already know it has a standard presentation. Let's take one. Then if we apply S to this standard presentation, we obtain another adjunction like this. And then if we further apply morphisms, flat morphisms from A to it, we obtain this adjunction. On the other hand, we can apply tensoring here with A. So we have A times E, A times int of A. And of course, A times E is just flat morphisms from this tensor, just again, the property of the object classifier. And now one can easily see that this and this guy is just a computation. They are equivalent, this and this. So to conclude, one just needs to check, okay, does this action doing first this and then this, and this action coincide up to this equivalence? If they do, the fixed points of the action, which are precisely this, must coincide as well. And indeed, one can check that these two actions are the same up to this equivalence. Therefore, the fixed points of the action, which are these two, are also coinciding. And that shows the property, right? Flat morphisms from A to S of E has the universal property that we require, which proves finally the theorem. And what about the algebraic geometry part of the story? Well, we do have that a huge amount of schemes are actually exponentiable. Any quasi-compact, quasi-separated scheme, which are very mild assumptions, then the quasi-compact, quasi-coherent, objects of shifts of X are exponentiable. In particular, this is the formula for the exponentiation. This exponential is just the modules over the locally finally presented quasi-coherent shifts. That is, those have an algebraic description, but they precisely coincide with the finally presented objects of this guy. So in the particular case, for example, if X is quasi-separated and Noetherian, then we have that the exponentiable is just the modules over the coherent shifts up. And if, for example, the case more restrictive, if A is a Noetherian ring, then this exponential is just the modules over the finally presented A modules. So this is all very fine, but it could even, we don't know, but it could even be that every scheme, not only quasi-separated and quasi-compact ones, are exponentiable in this categorical framework. But now the question would be, given a quasi-compact, quasi-separated scheme, do we have actually an honest scheme and not a non-commutative one, satisfying the desired property? We don't know this yet. We are trying to address this question, but it could be that it does exist. And then we have exponentiable objects within schemes, which is a subcategory, if you want, of the bigger non-commutative schemes. But it could be very well that exponentiability leaves the commutative framework. And then that you have that this guy is no longer quasi-co of anything. So this is an open question. And with this, I wanted to finish, and thank you all for your attention. And if there's any questions, I'm happy to answer.